So I'm going to briefly talk about, how IceCube sort of does its scope or creates this global grid, but sort of giving a context as well of what we're doing, why we're doing this in some ways. So to first order, so what is IceCube? IceCube is a neutrino observatory in South Pole. Compared to traditional astronomical observatories, we actually look for subatomic particles that come from cosmic or galactic sources. And to do that, we've instrumented about a cubic kilometer of ice with 5,160 optical sensors. And we're using sort of the natural medium that the South Pole, or rather the Antarctica, gives us in having a glacier of this size, but also having one of the purest, in a sense, optical media in the world, or that we know of actually, where a single photon or a single particle of light can travel up to 300 meters, which is unheard of, sort of in the normal realm, at least. Another thing that it helps us is also that the detector is sort of larger than its physical volume, so we can detect things that happen outside the detector, and then detect sort of a trace or a portion, or we sort of take a portion of the video in some ways that of this particle that travels through the detector. So here's a picture of our counting house that's on top of the glacier, but inside the glacier we have the instrument. So why are we doing this? So IceCube is actually a novel instrument in many fields. So we do astrophysics, so in the realm of neutrino astronomy, multi-messenger astrophysics, and things like that. So this is some of the NSF's one of NSF's top 10 big ideas here. But besides that, we also do sort of fundamental physics and earth sciences. So neutrino physics, so we studied the nature of neutrinos themselves, so how they oscillate between different flavors or different types of neutrinos, how they interact with matter, and then we also look for things that are what some would call beyond the standard model, so beyond what we can theorize, or what the standard sort of recipe book of particle physics has provided for us in dark matter and sort of all the various subtypes of potential dark matter. But also we also have some earth sciences, a mission in that we can study glaciology, where we have deployed sort of things into a glacier so we can study the progress of the glacier, but then also atmospheric science, so we can do some the atmosphere at the South Pole, but also above the South Pole with this detector. With all of these sciences, the big concern here is that we have lots of data to process in different ways. So these various different science goals ultimately require slightly different or completely different data processing capabilities. And also in sort of a particle physics sense, we do have Monte Carlo understanding of our detector, or rather sort of an internal understanding of our detector, and we sort of compare that to the data to find, to basically determine the science and the significance of the science. So sort of from a 30,000 foot view, this means that IceCube is mostly sort of classical particle physics computing. This means it's pleasantly parallel or ingeniously parallel. There's these what we call events or time periods of interests. But the issue is that the number of channels varies between these various events. So, ideally we would compute on a per event basis. But there are several caveats here that we need to understand. That there's no direct or continuous network link to the experiment. So we are at the South Pole. There is no, nice fiber line that goes to the coast or to other continents. We have these extreme weather conditions at the experiment. So, minus 40 degrees is considered warm. It's a desert. We require specialized hardware, so in this case, GPUs. And we have most of our software is developed in-house. So we have to, have a lot of development put in that. And of course, this large engineering, so we have a very broad science reach. And that leads us to some scheduling difficulties in terms of predicting resources that we need, the runtime of those resources, and things like that. So there's a sort of this difficulty of determining what we actually need in terms of resources. So we've created this sort of global heterogeneous resource pool. So you can see here from Madison out, we can reach resources that are across the world on basically nearly every continent. But we usually most share in opportunistic resources, meaning that, you know, we borrow a lot of resources from other people through Open Science Grid, shared in the sense that we get some allocation on a resource and we use that to do our computing. And again, you know, we have this mix of resources where, you know, we have these requirements. We need the GPUs. We also need CPUs. There's this broad physics reach, so we need a lot of we have a lot of uptime. So meaning our detector runs basically continuously, and we need to simulate that in real time. And of course, sort of our analysis software stack is in-house. So the standard packages that you use in particle physics don't necessarily support what we do, or we have these niche dependencies, what we heard earlier today. For example, Corsica is one of our other dependencies. And then across sort of the last decade of our operation, we've had significant sort of change in our requirements. First of all, sort of bringing in GPUs, then having multi-method astrophysics sort of added as one of our science drivers, and having a sort of issue with that. And you can see here on the bottom, for example, if this broad science comes sort of in a requirements range, so we can go, you know, from single digit memory requirements to over 100 gigabytes of memory that we require for some of our workloads. So how does IceCube actually work? So IceCube uses something called the shrink-off effect or shrink-off light. So this is similar to a sonic boom, but with light. So if you've ever looked at a nuclear reactor or seen a picture of a nuclear reactor, it glows in sort of this bluish light, and this is actually from the particles coming out of the nuclear reactor during the nuclear reaction. And similarly, you have neutrinos that can interact with the detector, and they give off some secondary particle, in this case a muon, which is just the heavier cousin of the electron. And as they travel through the light, they travel faster through the medium than light itself. So ice has a refractive index, so the light itself travels at about a third the speed, but these particles can travel at the speed of light. So during this, they give off this bluish glow in light. And that's one of the reasons why we basically need GPUs. Here's a movie of one of these particles traveling through a detector and giving off light, and every single one of these strands is an individual light particle or light, a photon of light that is traveling through a detector. And you can see that this needs significant computing time. So this is what some call ray tracing, and GPUs are basically very good at, you know, tiny tasks that are finite sort of in runtime, and this is sort of a perfect application for that, for the sort of parallelizability of this task. So looking again at the IceCube grid, sort of our sort of global computing presence. So back in 2016, we had this mix of grid resources, so Open Science Grid, European grid infrastructure, pledged resources, meaning we had some allocation on high performance computing clusters, mostly through NSF and Exceed. And then we had sort of also everything in between, where we opportunistically could access, you know, a cluster on a campus that is part of our collaboration. And so we had this weird mix of resources. The issue was that, of course, you know, we don't own a significant portion of these resources, so we can't make any demands on the local computing team. So, for example, the CE that we heard about yesterday and earlier today, so the compute unit that's sort of standard in the grid world is can't be deployed everywhere. So integrating new resources was really hard and resource intensive. Similarly, we experienced some scaling issues with our workflow management system. So at the time we used our sort of in-house written workflow management system. and that needed a significant amount of expert knowledge to deploy it and maintain it. These various different resources. And the issue there was, with this, because it was trying to do all the scheduling and all the sort of handling of data, plus the workflow, plus the scheduling. We saw issues that if we wanted to scale above about 3,000 pores, it was hard to potentially impossible. So we got a little bit over 3,000, and then basically the system just choked. At the same time, some technology like the hosted CE, so that's become popular with a significant portion of the newer resources on OSG wasn't really a thing at this point. So we were kind of stuck. So what we came up with is something that we call PyGlidein, which is based on the grid technology developed at CHTC. So basically, we took the idea that HTCondor is very, very good at scaling. We knew it could scale over 100,000 pores. There was this GPU and CPU support out of the box, so we could use a sort of heterogeneous requirements. But of course, there were these components that seemed, at least from our perspective at the time, a little too heavy or too hard to operate. So this is 5 years ago, so many things have changed, but we wanted basically a lightweight system to submit jobs out to these other facilities, and we came up with this concept of PyGlidein. Basically, why would we separate out the system? So as I said, the performance issues, we wanted to have this as lightweight as possible, so we can have this sort of grad student or postdoc or even an undergraduate could easily deploy this and sort of set it and forget it to first order. And we also wanted to, reduce sort of the burden of distributed resources for the individual users, saying, this all looks just like we have seen in Madison, where we just have a Condor queue, and instead of having this sort of completely separate system that people have to navigate. So basically, we borrowed a significant portion from the CHTC and the OSG architecture, and saying, we expose our job requirements or the job resource requirements somehow, and in this case, we did it through an HTTP and a JSON document. So basically, do a query on a data on a SCED, or rather a queue, and then you get sort of a reply of how many CPUs, GPUs, memory, disk, these various job needs. And then at the remote side, or at the other side, basically we just submit a job that has the right resource requirements. And once that job executes, it basically runs a Condor start D saying, okay, I'm alive, and it connects back to our big sort of HTCondor pool. What is sort of borrowed here is that we took out sort of the gliding WMS idea of things, in that we sort of simplified this down to sort of the bare bones. And and by that sort of simplify the system that even, an inexperienced user could really deploy this. And of course, there is some overlap in terms of, wasted resources that, we have multiple jobs being started at different sites with the same requirements, but ultimately, we have so many jobs that either A, they'll be picked up by somebody else, or B, that, if we don't use a resource, they will die within, a few minutes of knowing that there's nothing to sort of work on. So from a user perspective, this really looks more like, an HTCondor pool plus the data management. So we want it to look like just an HTCondor pool. From an operator perspective, there's sort of this minimal overhead in adding a cluster to the pool. So, experienced users can do this in a day, if not less, depending on the cluster and its sort of specifics. Again, we get a lot of the tooling that's already around Condor, so the monitoring and all these various other things we get for free. And sort of the biggest portion for us is that we didn't need this sort of what we felt heavyweight compute element, but rather we just needed either SSH or cron, or a cron job for the submission. So that was really sort of a very low barrier to entry for a lot of users in a lot of places. There's some future improvements. This is an organically grown code and sort of user continuous support, and I'll go into what that means in a bit. So, so sort of summarizing our experience in the last 5 years, most of our external IceCube resources that we access, either that are pledged HPC resources or other resources that we get contributed, run on this system. So most of the time, we still get a significant portion of our resources opportunistically or through OSG, and then we just straight go through CHTC. It has been remarkably stable for how much time and power we've invested into this system. I mean, this is literally sort of a few week or maybe a few month effort, and then since then it has sort of organically been maintained and very little sort of time investment, because we basically let the HTCondor do the heavy lifting. How to aggregate the resources, how to schedule on these resources, how to sort of slice and dice the various resources that we get according to what our researchers need. And then of course, the experience of the high energy community, and also the community that we just heard about, is basically where we get our solution, our problems and solutions, and that somebody has most likely run into the solution this problem before, and we can sort of ask our friends over at CHTC to help us out. And of course, the other big thing is kind of the feature stack moves of HTCondor. So we got GPU support, and we got this resource splitting support, the third-party data copy that's now coming in HTCondor 9, and ID tokens is kind of, we don't really have to do much besides sort of update HTCondor to get all these features, and that's reduces a lot of our effort there. And of course, sort of our biggest issues have not been with HTCondor, but rather sort of the remote site, or the site we want to compute on, where there's a network connectivity issues. So either they're very strict, or we have to get some special exemptions, or there's sort of invalidability of our software. But now with containers, this has been solved as well through our help of our friends at Fermilab. And then, the biggest hurdle we have seen so far, besides the network connectivity, is that there is no cron and MFAs, or we have a two-factor authentication system. So we either can't SSH in automatically, or we can't submit jobs automatically. We've only had, a handful of sites where this has been an issue. So if we look at those usage statistics over the last 2 years, and you see, we can easily scale with the cloud success use. You can see that, the last 2 years, the size of our resources, especially on the GPU side, has increased significantly since about since about late 2020. So we've added new resources very elastically, and they've provided a significant amount of computing, and without much or any work really, this has scaled. We now consume about 7 million CPU hours every month, and about 700 GPU hours per month, 700,000 GPU hours per month. So you can see, even if we double our GPU capacity, we didn't really have to do anything besides, deploy these new sites, and then they run basically automatically. And most of this sort of is to the credit of Condor just being able to handle this to first order, without us having to do a lot of fine tuning of the VMs or any of the other things. So in terms of future plans, we're actually taking another page out of the book from OSG. We want to remove our sort of private Glidein and just employ the OSG Glidein pilot and the container that comes with it, just because using sort of shared resources reduces the burden on us, but also gives us the ability to kind of give back to the community. Now with ID tokens being being sort of out of the box and ready for prime time, we need to change that for our pool authentication, so we can do a lot more more detailed authentication rather than just shipping around a pool password. We would like to a little bit to optimize our HTTP server, just to sort of you know, come up to 2021 rather than still living in a couple of years ago. And the big one for us is user container support. So Condor already has this to first order, that, you know, you define a singularity image and what you want to execute in that image, but we haven't exposed that in our HTTP server yet. So they have been sort of this compatibility issue where, you know, you're running a Glidein. So it's hard to require a certain base container. So we need to be sure that, you know, we can run HTCondor inside this container, or, you know, of running containers inside containers is a little bit is a thing that we're running into. So we need to really think about a solution there in terms of how to you know, how to make that happen. But I mean, currently we still have a limited number of people who are actually looking for these sort of containers. But, you know, with third-party copy and things like that, I think we'll see a higher sort of user in the things. And with that, I'll open the floor for questions.